Thank you. And first, I would like to thank the organizers for giving me the opportunity to talk here this morning. So as you can see, the title of my talk is Qubit Hamiltonian Extraction for Superconducting Circuits using the Schriffer-Wolff transformation. And it's going to be about a numerical method that I've been using during my first part of the PhD that helped me. And it can map a circuit Hamiltonian into a more economical spin description of the system. And it uses the Schriffer-Wolff transformation theory. And in this presentation, we will see some numerical results that I've got, and that also include kind of non-stochastic interaction between two qubits. So let me start with a summary of the presentation. So at first, I will just say a couple of words on why we need Hamiltonian reduction and effective Hamiltonians. Then I will talk briefly about some of the standard tools that people use to understand how flux qubit works in terms of energy spectrum, for example, numerically. And then I'll show how the Hamiltonian reduction method applies first to single qubits and then to multiple qubits using the Schriffer-Wolff transformation. And then I'll have some numerical results with two qubits both inductively and capacitive coupled. So why do we need reduction? It's because quantum many-body systems and systems described by continuous variables are quite challenging to model with computers. So nowadays we need supercomputers. And of course, we all hope that one day we can replace them with a quantum computer. So, but in the meantime, we need some kind of more economical description of our system. So if we start off with a correct, complete description described by an Hamiltonian H, we want a smaller effective Hamiltonian that basically neglects all the higher degrees and higher energy degrees of freedom of the system. This is exactly what happens when we talk about flux qubits. So we have a superconducting circuit, like this is an RF qubit. It's a superconducting loop interrupted by a Josephson junction. So it is described by continuous variables, the flux and the charge associated with the loop and the junction. But at the end of the day, we want to look at these and use it as a two-level system with only two states with opposite circulating current. So to do Hamiltonian reduction, we first need the best expression for a correct Hamiltonian for the system. So in this case, I'm going to assume that the superconductor remains in its ground state. So there are no quasi-particles excitations. And in this case, the Hamiltonian is just the circuit Hamiltonian that contains the inductive, capacitive, and Josephson energies in the system. So the usual way to calculate this, or at least one of them, is to identify nodes in the circuit, associate each of them with a pair of non-commuting operators, quantum operators, the flux and the charge. And with all of this set of operators, we can write the Hamiltonian of the circuit that contains a capacitive term that's written in terms of the inverse capacitance matrix, an inductive term with an inverse inductance matrix in front, and then the nonlinear terms coming from the junctions that have this cosine form. And now, if we want to write these in a code inside a classical computer, we need to express these operators in form of a finite matrix. So one possible way to do it is for every mod operator, flux and charge. In this case, I'm using the ladder operators to re-express them. And then I expand the ladder operators in the occupation number basis, and I throw away an infinite number of states with occupation number greater than n max. Okay? At this point, if we say look at the spectrum of this system for a particular set of physical parameters, we see that as we increase the n max that we used for every mode in the circuit, the spectrum that we find by diagonalizing the Hamiltonian converges towards the correct spectrum of the system. And this red line shows us how the computer makes more and more of an effort, of course, to do this, and so the time it takes to find a solution increases. Once we know how to find the spectrum of the system for a given set of parameters, we can think of doing other things like varying parameters in the system, like in this case, the flux in this qubit loop, and see how the spectrum changes as a consequence. And so these are the first few low energy states of the system, and the ground state has been subtracted actually. So these are like transitions energies from the ground state as a function of flux. Then for Hamiltonian reduction, we want to focus on the two lowermost energy states of our system because we want it to be a spin. So there's an easy way to get a Hamiltonian that has these two same energy eigenvalues, and this is just this one because we've solved the eigenvalue problem, so we can write the Qubit Hamiltonian in this form in the eigenbasis of the circuit Hamiltonian. But this is not particularly interesting, especially because in quantum annealing at the end we want to measure in the persistent current basis. So we would rather have an expression in a persistent current basis. So we need to define that basis. So numerically, we can look at the current operator associated with the qubit loop here, project it in the low energy subspace of the circuit Hamiltonian, and find its two eigenstates that have opposite persistent current eigenvalue. These are our computational states 0 and 1. Once we've found them, we can use the relationship between 0 and 1 and E0 and E1 to rotate our Hamiltonian, our qubit Hamiltonian, in the computational basis. And so we retrieve our usual transverse field Ising model of the qubit. This is the expression of the delta and epsilon parameters as a function of the parameters I had before. But an easier way to calculate them is by using this property of the Pauli operators and using basically these Hilbert-Schmidt product kind of projection. So if we apply this method to the system we've seen previously already, we see that as a function of the applied flux, around 0.5 flux quanta, we increase the longitudinal field linearly, and while the transverse field remains fairly constant, at least in a small region here. And what's good about this method is that if we now diagonalize these 2x2 qubit Hamiltonian, we get exactly the same spectrum as the two lowest energy eigenstates of the original circuit Hamiltonian, as we can see here. So to recap, for this single qubit case, we need to solve the eigenvalue problem for this circuit Hamiltonian. Then we need to solve the eigenvalue problem for the current operator to be able to rotate the qubit Hamiltonian in the computational basis, and so determine the Ising Hamiltonian coefficients. Now, for multiple qubits, things get a bit more complicated. For example, let's focus on this system of 2 3-junction qubits interacting magnetically with a tunable inductive loop. So it's a compound junction RF squid. In this case, the energy of the system is described by this Hamiltonian that has the independent Hamiltonian of the two qubits and the coupler, plus an interaction term. So just like for single qubits, we would like to define the qubit subspace as that space spanned by the two lowest energy eigenstates of the qubits. And in this case, we want to take the outer product with the ground state of the coupler, right? The problem is that when we introduce interactions in the problem, the states inside the just defined qubit subspace are mixed with states in its complement. So we need a way to separate, to retrieve the original qubit subspace. So let's now make a couple of assumptions. So first, we assume that these four states, four-dimensional space spanned by these eigenvectors is also the one spanned by the lowest four energy eigenstates of the complete independent unperturbed Hamiltonian. So this means that if we look at the energy spectrum of the qubit Hamiltonians and the coupler, we find the lowest two qubit states and the ground state of the coupler. We get four combinations of states, and these four combinations of states are separated by any other excited state of the system. The second assumption we make it's not going forward, sorry. It's not responding even from here. Oh. Okay. Yeah. So sorry, the second assumption we make is that now, in this case, the fifth energy eigenstate of the system is sufficiently far away from the fourth compared to the magnitude of the interaction part of the Hamiltonian. So this means that when we introduce the interaction in the Hamiltonian, the qubit subspace goes into a new subspace with the same dimension. And graphically, this means that the fifth state here is far enough that when we introduce the interaction, we still have, four states there at the bottom, separated by the others. And so now the Schriffer-Wolff transformation theory tells us that since these two subspaces have the same dimension, we can define a rotation between them, which is called the Schriffer-Wolff transformation. And with that, we can define an effective Hamiltonian of the system that has the same low energy spectrum of the original Hamiltonian and only acts on the qubit subspace. So by definition, this will be our qubit Hamiltonian. So to find the Schriffer-Wolff transformation numerically, I use this definition from this Briavi Di Vincenzo loss paper. And all we need is to find these two projectors on H qubit and H qubit prime. And so we need to find, in this case, the lowest four energy eigenstates of H node, the unperturbed Hamiltonian, and H, the total Hamiltonian. And you might be asking how we can write the full Hamiltonian of the system. Well, we need a way to reduce the size of the Hilbert space. So I use what's called sometimes adiabatic elimination to do it. And then we can expand our effective Hamiltonian in terms of Pauli operators of different orders up to n for n qubits. And again, use this property of the Pauli operators to find the coefficients from the Hamiltonian by taking the trace. So brief recap. So in this case, we solve the eigenvalue problem for the independent qubit and coupler Hamiltonians. Then for the current operators associated with the qubit loops to find the Pauli operators. Then we find the lowest 2 to the n for n qubits eigenstates of both h0 and h to determine p0 and p, which allow us to calculate the Schriffer-Wolff transformation U, and then the qubit Hamiltonian. And finally, we can find the coefficients of the Pauli operators there. So let's see a numerical example, the system we've seen before. This value alpha is the ratio between the small junction in these 3 junction qubits and the large junctions, and it's 0.8 in this simulation that I'm going to show. So I'm going to introduce fluxes, alpha flux quantum in both the qubit loops, and a varying flux in the X loop of the coupler. And we see that the spectrum of the system changes as such. And in this case, it's quite easy to see what's happening. It's that the ZZ interaction is varying with the bias point of the coupler. And the spacing of these 2 sets of 2 levels is just twice the ZZ coefficient. But using the method I've described above, we can do the same and extract directly the coefficients. We see that all coefficients are 0 here, except for the one in front, sigma Z1 times sigma Z2. And now, as a sanity check, we can diagonalize the 4x4 qubit Hamiltonian and see that its spectrum matches the one of the circuit Hamiltonian perfectly. So now something a bit more interesting. We decrease the size of the small junction in such a way to have finite transverse fields in these qubits. Now the spectrum of the system as a function of the flux in the coupler loop is a bit less obvious to interpret, but using our Hamiltonian reduction method, we can see that in this case, yes, we are varying the size and the sign of the 2 local ZZ interaction. And we are also changing the transverse field of the qubits as a result of a varying inductive loading of the qubits. Also, we see a small component of XX interaction in this case. Again, our sanity check works for this system. And finally, I thought I would introduce capacitance between these 2 nodes in these 2 flux qubits with 100 femtofarads sides. In this case, the spectrum looks like this, and the coefficients of the Ising Hamiltonian are these ones. So again, we see a varying ZZ interaction, transverse fields here in yellow. Then this red line is an XX interaction, and the purple line is a YY interaction. So we've realized a Hamiltonian that is non-stochastic in these green regions, where the magnitude of the YY component is greater than both XX and ZZ. And this has been shown also experimentally by D-Wave, and it's in this preprint, and we've seen it in this conference. Again, our sanity check works. So the spectrum of the 4x4 qubit Hamiltonian matches the one of the circuit Hamiltonian. So in conclusion, I think I've showed a fairly simple and general numerical method to reduce the Hamiltonian of a system of flux qubits to a spin Hamiltonian. And this has potential applications in getting information about our annealing schedules, more precise ones, in particular, understand crosstalk between, as we vary the Z-Z interaction, we saw that we affect the transverse fields, for example. Also, we can find non-stochastic terms and even many body terms, even though I haven't shown this in this presentation. So the method is based on two intuitive assumptions, and it's a direct application case of the Schriffer-Wolff transformation theory. And in the near future, I would like to test possible limitations of this approach in terms of scalability and maybe applicability to different kinds of qubits, like maybe Josephson phase-leap qubits, where the Hamiltonians of which cannot be made real, as in this case. And also, I would like to consider dynamical effects, because we are all here and interested about adiabatic quantum computing. So there is a theory of time-dependent Schriffer-Wolff transformation that might be useful here. So finally, just a photo of the people in my group. You might recognize the location of it. And here I have a few names of people that have helped me develop this thing. And thank you for your attention.
Hello, thank you very much. In the original paper by Bravier et al., the Schrieffer-Wolff transformation paper by Sergei Bravier and his co-author, they did analytic analysis, and you're doing numerical analysis. I mean, they'd done analytic, anyway. In the numerical analysis, if you have 100 qubits, then you have 2 to the 100. The eigenvalues in your numerical analysis, you said something about this adiabatic elimination, but there was not so much details about it. How do you reduce the 2 to the 100?
Okay, yes. You can do it for at least a small enough number of qubits. I don't know how big exactly.
Yeah, then you don't even need adiabatic elimination. If it's small number of qubits, 5 qubits, then it's 32. I can fit that on the classical computer.
Yeah. This is how adiabatic elimination works in my case.
This was in the presentation?
Familiar with it? No, it's a back slide, kind of. So you basically write the interaction part in the Hamiltonian that here contains like an operator acting on the first qubit and on the second qubit, considering now just 2 qubits interacting with each other, with nothing else. And basically, we first diagonalize the single qubit Hamiltonians, the unperturbed ones, and find a number of eigenstates, and then project these 2 operators, O1 and O2, on these eigenstates, as you can see here. So we can choose now the number of eigenstates we are keeping, and now the size of the Hamiltonian is just n1 times n2 instead of the original. You could start with 1,000 by 1,000 here, 1,000 by 1,000 here, and this would mean that this is 1,000,000 by 1,000,000 elements. But here you can reduce everything, and there is some level of approximation here. You see that there are additional contributions that you can calculate if you want. So this is how it works specifically, but I think there's an intrinsic limitation to the Schriffer-Wolff scalability, which is in the size of the gap. If the interaction is so big, and if you have many interacting qubits, the interaction size scales probably linearly with the number of qubits at least. So it's intrinsically not scalable to very large systems, so it's more useful for maybe test bed applications, or you can do it maybe the transformation locally on a number of nearest neighboring qubits.
Yeah, this all depends on being able to split the Hamiltonian into the low-lying energy levels and the high energy, and being able to actually do that split. But I think your work is really great.
Thanks.
Is it possible to perform the inverse of your scheme, which is to say to assemble a series of qubits to approximate a continuous system, at least mathematically?
A very good question. I can only think right now of optimization kind of schemes or machine learning maybe schemes. You could try and change parameters in the system until you find the right coefficients.
So this Schriffer-Wolff transformation is not a good way to obtain the parameters to approximate the original continuous
Yes,
potential. So you're saying that?
I guess it should be invertible, I guess, but I never considered this
Okay, thank you.
possibility.